Okay, welcome back to the South Notts Amateur Radio Club Foundation course. This lesson is going to be on transmitters and receivers. As we go through the slideshow, please feel free to pause the video at points where you need to re-go over any of the information, and we'll begin here. So this part of the course is on modulation types and waveforms, sidebands, block diagrams, software-defined radios, and station setup. If you do get stuck on any of these topics and you'd like further help, again, please feel free to review this video again, or alternatively seek additional help from your tutor. Will be happy to help you out further. So, beginning off with radio frequency signals, a radio transmitter is used to send information from one place to another using electromagnetic radiation. A transmitter creates an RF carrier wave on the required frequency and mixes in the information to be transmitted. This is called modulation. A carrier wave, as you can see here, is a consistent wave, even all the way through, at a particular frequency. When that wave gets modulated, it can be modulated by AM, which stands for amplitude modulation, amplitude meaning height. So as you can see, it would go greater in height and depth, and then thinner, and then wider, and then thinner. So we can alter the thickness to create our sounds, if you like, or we could alter it in frequency, where it's all the same amplitude. However, the frequency, like an accordion, gets squished in or stretched out, and the sound can be modulated in that manner as well. So if we try and transpose an audio signal onto a carrier, as you can see here, this is for an amplitude modulation. We have the audio signal there, a wave, and that would be representative of a voice. And we have the carrier signal, which is a radio frequency, which again is a consistent frequency. And when the two get added together, you'll see that the carrier frequency is still there, but it has been squished and stretched to represent the audio signal. And this is how audio signals are modulated in amplitude modulation onto a carrier. There's also FM, frequency modulation, and this is the equivalent for frequency modulation. So we have the audio signal and the carrier as before, but instead of modulating the amplitude or height, size, up and down, thinner and thicker, we've got consistent height, but we've got a closer, thicker frequency at the peaks where the audio signal goes up to the top, and then we've got much more spread out frequency at the troughs of the audio signal. So looking at the modulated signal at the bottom, you'll notice it becomes very tightly spaced at the peak of the audio signal directly above, and as the audio signal goes down and into the valley, you'll see the valley part of the modulated signal is stretched out. And so we're representing the highs and lows of the audio signal by compression and extension of the modulated signal, a bit like a slinky spring. So when we look at waves, we will notice here that the audio signal is comparatively low frequency. There's only a few gentle waves in there. An AM signal is also represented by the wave overall shape. However, the actual wave inside, the wave creating the shape, is of the higher radio frequency. And the FM signal, again, is consistent height, and it's the tightness of the frequency that represents the peaks and troughs of the audio signal. So it is going to be important to remember these shapes and which one corresponds with what type of modulation, as you may be asked this question in the exam. It will show you a picture and say match this picture up to AM, FM or audio, or vice versa. With Morse and Data, we also get a signal representation like this. The Morse code audio signal is essentially like a series of steps. These blocks are very square and straight, and with Morse code you're either sending a carrier or you're not sending anything. So it's either dead or a carrier, and then dead again, and then a carrier, and so on. So to the ear it sounds like on and off. You'll have a consistent noise when it's on and no noise when it's off. And if we look at the signal, the CW signal there on the second line below, you'll notice you'll see the frequency happening when it's on and then nothing when it's off. This CW signal would be an RF signal, so you wouldn't hear that. This is representing the actual RF that's sent out over the air. So with CW, Morse code, the tones are switched on and off using a Morse key. So when you press the key, it gives out a frequency, and when you let go of the key, it turns it off. With data, you will get audio tones, usually multiple tones, generated via an audio interface or a computer sound card. And these are usually quite melodic, and it's not a single tone, it's multiple tones at different frequencies, different pitches. So next we're going to take a look at sidebands. For amplitude modulation, modulating the carrier results in something called a sideband being created. Signals adjacent to the carrier itself. Looking at this diagram, you'll see the carrier down the middle, so that is the frequency that's produced by the radio, and then we will have a lower sideband and an upper sideband. The signal bandwidth altogether is the total width of all those three individual components, and this is for AM, amplitude modulation, which has a lower sideband, an upper sideband, and a carrier. And this is considered fairly wide bandwidth. As the information in the upper and lower sidebands is the same, you can just transmit one or the other. So you'll see the notation SSB, or single sideband, used often. Instead of transmitting the two sidebands as in AM, you'll get better results using all of your transmit power using just one sideband, either the lower sideband LSB or the upper sideband USB. So if you imagine here you were throwing a ball, if you had a ball that weighed the equivalent of an upper sideband, a carrier and a lower sideband, there's three items in there. It's going to be heavier and not throw as far as if you just had one out of the three, and this is the same principle here. We would cut off the carrier and one of the sidebands to leave just a single sideband, and therefore because it's a equivalent or a lighter weight, it will throw further and you'll get better distance with your signal. So for single sideband operation, note that the lower sideband is normally used below 10 MHz. You could use either, but it's general practice that lower sideband is used below 10 MHz. Above 10 MHz, it is normal practice to use upper sideband. There's no law against this or law stipulating this, but it's of general convention that if you're above 10 MHz, people will be listening and transmitting on upper sideband, below 10 MHz, lower sideband. So this is just convention. Next we're going to discuss transmitters. A radio transmitter's got four basic stages. The first stage is the audio stage. This gets and amplifies weak signals from the microphone. The next stage is the frequency generator. This creates the radio carrier signal on the right frequency. These signals are then passed to the modulator, which mixes the radio and audio signals together. And then we have the RF power amplifier, which amplifies that modulated signal. and sends it out. Apologies for this, it seems to have been chopped off the bottom of the presentation here. So next we have a transmitter block diagram, and this shows those stages. On the left of the diagram we have a circle with a flat line, and as we know from our previous symbols lesson, this represents the microphone. The microphone is connected to the microphone amplifier or audio stage, as we mentioned on the previous slide. Box number 2 is the modulator, and as you can see it's connected to box number 1 and box number 3. Number 3 is the carrier oscillator or frequency generator, and so box number 2, the modulator, is mixing these two inputs to create a modulated signal. That then passes to box number 4, which is the radio frequency power amplifier, which will take that small modulated signal that we've produced and magnify it dramatically to send out over the aerial and through the air. On the diagram on the right hand side, you'll notice that crow's foot diagram, that symbol which represents the antenna. For an AM transmitter, the block diagram looks like this. So we have the 4 stages, and as we've seen on the previous slides with the shapes of the waveforms, you have the microphone amplifier giving the audio signal. We have the carrier oscillator with the consistent RF frequency. We have the modulator, which modulates the two together. And we've got the RF power amplifier, which, as you can see there, increases the size of the signal to go out through the antenna. A diagram similar to this or the previous slide may be asked on the exam with numbers in the boxes saying name box 1, name box 2, etc. So this is something important to learn. The next stage is transmitter operation. As we can see from the diagram, we have the 4 boxes there, and if the oscillator that produces the radio frequency is not set correctly, you may accidentally transmit outside the animator band and cause interference. This is important, and it's a critical part of your license that you do not transmit outside of the amateur bands. So we must make sure the oscillator is set correctly so that you are on the frequency you intend to be on. The RF power amplifier must be connected to a matched antenna. If it's not, it may damage the transmitter. We're going to talk more on matching in our antenna module. Transmitter audio levels. Excessive amplitude modulation can cause audio distortion and interference with adjacent channels. Excessive frequency deviation causes interference with adjacent channels as well. We must make sure that we set the microphone gain correctly, and if we're using a data mode, we need to check the audio levels from the computer are not too loud. From our license conditions module, we know that at Foundation you can only use commercially purchased transmitters. You are not allowed to use a constructed transmitter. You must only transmit on allocated frequencies and must not exceed permitted power levels. And you must stay in band, not causing interference, and you must test your transmitters from time to time. You may also get a question in the exam about this, and from time to time is an important phrase to remember. Next, we're going to discuss receivers. A radio receiver recovers information sent from one place to another using electromagnetic radiation. The process of recovering the audio information from a modulated RF signal is called demodulation. As you can see there at the bottom, we have an FM signal. So this is a modulated radio frequency coming through. As you can see, it's not even. There are constricted parts and extended parts, so there is an audio form transposed into that signal, into that carrier. So receiver basics. A radio receiver has three basic stages. The first stage is the tuning and radio frequency amplification. This stage tunes into the required frequency and it amplifies the weak signal so it can be used. The second stage is the demodulator, or sometimes called detector stage. This extracts the audio from the radio signal, often called demodulation. There are different types of detector for each modulation type. The final stage is the audio amplifier, and this amplifies the audio signal and feeds it to a loudspeaker or headphones. Here we have the receiver block diagram, and as you can see, this is essentially the reverse of the transmitter. So on the left we have the antenna bringing the signal down and into the stage 1, which is the tuning and RF amplifier. This will tune in the signal, usually using the VFO, the knob on the radio, and it's going to amplify that weak signal to be used in the following stages. Stage number 2 is the demodulator, so this is going to remove the audio from the carrier, and finally that audio is going to be amplified through stage number 3, which is the audio amplifier, which then goes to a loudspeaker or to headphones. Here's an example of an FM receiver block diagram. And as you can see, we have the antenna bringing a signal into the tuning and RF amplifier, and you can see the signal is merged with the carrier in that box. The detector removes the carrier to leave just the audio signal, as we see represented there. And finally, the audio amplifier greatly increases the size of the signal so that we can then listen to it through the speaker or headphones. Next, we're going to discuss software-defined radios. Software-defined radios are increasingly commonplace, ranging from low-budget receivers that plug into a computer's USB port to large, expensive desktop transceivers. SDRs receive electromagnetic signals from the antenna and digitize the signal for processing in software, not hardware. Incoming signals are converted from analog to digital, also known as A to D. A mathematical operation in the SDR enables all of the radio signals to be sifted into separate frequency components. The required signal is then selected using a filter defined in the software itself. Demodulation is carried out in software also, and the resulting signal is converted from digital back to analog, or D to A, for a speaker or headphones to then play. The diagram below shows that process. So the signal comes in through the antenna, which is an analog signal. It is converted from analog to digital. It's then processed digitally by the computer, and then it's passed back from digital to analog to play through the speaker. SDR transmitters. With transmitters, the speech is converted from analog to digital. The modulated radio signals are generated using software. The resulting signal is converted from digital to analog, then amplified and fed to the antenna as per the block diagram below. So microphone signal in, converted from analog to digital, it's processed digitally and then converted from digital back to analog. It's then amplified with the power amplifier and sent out through the antenna. Next, we're going to look at station setup. For an HF station setup, the foundation course includes a practical on connecting a transceiver. This will include connecting a power supply, a transceiver, including the microphone, Morse key, data interface, etc., an RF filter, an SWR meter, an antenna matching unit, and an antenna. And this will be done on the practical part of your course. So in summary, we've seen the block diagrams. We need to remember the diagrams for transmitters and receivers, since there's almost certainly a question in the exam on these. It's important not just to learn the numbers, but to learn the meanings of what each stage is. We've discussed the modulation types, recognizing amplitude modulation and frequency modulation, and we need to remember single sideband, lower sideband, and upper sideband. We also need to remember that software-defined radios do all their processing in software, not in hardware, meaning that it's processed in a computer using a computer software program as opposed to moving through actual components. Then we've discussed transmitter usage. We don't want to transmit out of band, and particularly with digital modulation, we want to watch our audio levels. We don't want to over-modulate or over-deviate. At this point, if you have any questions, please review the video again, and if you still have unanswered questions, contact your tutor and they'll be happy to help.